Have you ever felt like math just has these random rules you have to memorize? Like why on earth are there 360 degrees in a circle? Well, in this explainer, we're going to pull back the curtain on that and discover a way more natural and frankly more powerful way to think about circles, the radian. So if you're heading into trigonometry or calculus, you are in exactly the right place. Let's dive in.
So let's start with a pretty bold idea, and this quote just nails it. The way most of us first learned to measure angles, with degrees, it's not the most fundamental system. It's totally a human invention, a convention that works, sure, but it's not the language that circles and waves and rotations actually speak out in the real world.
To really get why radians are such a big deal, we first have to take a good hard look at the system we're all used to. We gotta question what we know and ask about the limits of using degrees.
Have you ever really stopped to ask that question? Why 360? It's not because of some deep geometric truth. Turns out, the ancient Babylonians probably picked it just because it has a ton of divisors. You can divide it by 2, 3, 4, 5, 6, 8, 9, 10, 12. You get the idea. It makes the math easy, which is convenient, but it's also completely arbitrary.
And that brings us to the most crucial point. We need a unit of measurement that isn't just something we made up, but one that comes naturally from the properties of a circle. And that's exactly where the radian comes in. It's a measurement a circle gives to us instead of one we force onto it.
So, how do we actually build this new unit? The really cool thing is we can do it in a super intuitive way. Let's just forget about formulas for a second and just picture a circle and a simple piece of string.
Okay, so imagine you've got a circle. It can be a tiny little circle or a massive one. Doesn't matter. Measure its radius. The distance from the center straight out to the edge. Now just cut a piece of string that's exactly that same length. Next up, you take that piece of string you just cut and you lay it right down on the circumference, the edge of the circle. The arc that you've just covered with that string, well, that creates an angle right back at the center of the circle.
And boom, there it is. That angle you just made, that is 1 radian. It's this perfect natural relationship defined right there. When the length of the arc is the same as the length of the radius, the angle in the middle is 1 radian. And the best part? This works for any circle, no matter how big or small.
Okay, so that leads us to the most important question for actually using this stuff. If that little piece of arc is 1 radian, how many of those radius length strings would it take to go all the way around the entire circle?
Well, think back to your old geometry class. The formula for circumference is 2 times pi times the radius. So what does that tell us? It means it takes exactly 2 pi of those radius length strings to wrap around the whole thing. And that gives us our absolute cornerstone conversion, the one you've got to remember. 360 degrees is equal to 2 pi radians. Once you know that, everything else just falls into place. A half circle, 180 degrees, well, that's just pi radians. A right angle, 90 degrees, that's half of that, or pi over 2 radians. See how it works?
Okay, let's make this less abstract. It's time for some examples to see how this simple relationship is the key to actually solving some problems.
Let's start with a basic one. Imagine an arc on a circle is 15 centimeters long, and the circle's radius is 5 centimeters. How big is the angle? Well, you just ask yourself, how many radii fit into that arc? 15 divided by 5 is 3. The angle is 3 radians. Simple as that. And notice how the units, centimeters, just cancel out. That's because the radian is a pure ratio, which is part of what makes it so useful. We can also just flip that idea around. What if you already know the angle and the radius, but you need to find the actual physical length of the arc? Well, it's just a simple multiplication. So say we have an angle of 1.5 radians on a circle with a 10-inch radius. The arc length is just 1.5 times 10, which gives us a 15-inch arc. Easy. And finally, we can even solve for the radius itself. Now, don't let the pi symbols scare you off here. They're just numbers. If an angle of pi over 4 radians carves out an arc that's 3 pi over 2 centimeters, we just divide the arc length by the angle. The pi's cancel each other out, and we find out the radius has to be 6 centimeters. All right, so with any new concept, there are always a couple of common hurdles. Let's make sure you don't trip over these when you're first getting started with radians. This is by far the biggest mistake people make. They forget just how big 1 radian is compared to 1 degree. 1 radian is over 57 degrees. So if you see a problem that says an angle of 2 and there's no little degree symbol, you have to assume that means 2 radians, which is a really wide angle, way bigger than a right angle. The second pitfall is treating pi like it's some kind of special unit or a variable. It's not. Pi is just a number, approximately 3.14159. So when we say pi radians, we literally just mean about 3.14 radians. It's a quantity, not some special type of angle.
So, after all that, you might be asking, why did we go through all this trouble to learn a whole new system? The answer is because this isn't just some academic exercise. Radians are absolutely essential out in the real world.
Remember that simple formula? Arc length equals radius times angle? That right there, that's the magic. It creates this perfect, seamless bridge between rotation and linear distance. It's how engineers can tell a satellite how many miles it's traveled just by knowing its angle of rotation. It's how your car's speedometer turns the spinning of your tires into miles per hour. It is the absolute backbone of almost every formula in physics and engineering that deals with something spinning.
And that really is the ultimate takeaway here. Getting comfortable with radians isn't just about passing your next test. It is the language of rotation. If you're moving on to calculus, physics, or any kind of engineering, being fluent in radians is completely non-negotiable. It's the key that unlocks the math behind literally everything that spins, oscillates, or moves in a wave. So the real question is, what doors are you going to unlock with it?